All right, thank you for the introduction. So I'm going to get started with some motivations, in particular looking at S-boxes, which are key components of most ciphers because they provide nonlinearity to your cipher. So an S-box is typically defined through lookup tables, and it's basically a function which takes typically 4 bits and returns 4 bits. So for instance, here you have the S-box for the rectangle cipher. It's a S-box, and here I have a quote from the paper describing how this S-box is specified. However, when you implement your algorithm, you cannot use such a lookup table because lookup tables are vulnerable to cache timing attacks. Basically, the idea is that repeated access to your tables, which is stored in memory, leak information on the secret data you are encrypting because of cache hits and misses that an attacker can observe. And deduce information on which data you are encrypting. So what you can do instead is to use a circuit to compute this S-box. For instance, here you have a circuit which takes 4 bits of input, which goes through about 12 logical gates and compute 4 bits of output, which are the same as if you had done a lookup in your table. However, in this talk, we are not interested in generating hardware. We are at the software level, so the circuit would be a dozen C instructions doing logical bitwise operations between your inputs. Now the question becomes, how do you make this efficient? Because at first you just had to do one lookup in your table, and now you have to compute 12 operations to compute your S-box. And that's where bitslicing comes in. Let me show you in a small example what bitslicing is. Let's assume we have an input stream of some 3-bit data. We are going to need 3 registers to store them, and each bit of our input is going to go in a different register. Now, there is a lot of empty space in our registers, so what we can do is to take the second input, independent of the first one, and put it in our registers as well. And we keep doing the same thing until our registers are full. And now, when we do an operation between 2 registers, we're actually computing 4 times the same operation at once. For instance, a XOR between the first and the third registers computes 4 XORs at once. Now, if instead of some 4-bit registers, you use some very wide register provided by SIMD instruction sets, for instance, AVX 512, you can compute 512 times your instruction at once. So your S-box, which at first was just lookup in a table, now it becomes 12 instructions, but those 12 instructions compute 512 times your S-box at once, and that's very efficient. Now in practice, a real bit-slice algorithm will look like this. You're not really supposed to read it. It's a snippet of code extracted from the code of bit-slice implementation of DES. So why is it so unreadable? Well, DS takes an input on 64 bits, which once you bit slice it becomes 64 variables. So at any point in your program, you are dealing with 64 variables rather than a single 64-bit variable. On top of that, C compilers are not very good at optimizing such codes. So the guy who wrote that code did a bunch of optimizations by hand, and you end up with this kind of code, which you can't really read or debug or do anything with it except run it and pray that it works well. So that's where Usuba comes in. Usuba is a programming language designed to write ciphers and generate bit-slice code. So on the example of the rectangle cipher, on the left you have a pseudo-circuit describing rectangle, and on the right the Usuba code expressing the circuit. And the idea of an Usuba program is that your Usuba code is a straightforward translation of your pseudo-circuit of your cipher. So you see a rectangle takes a plain text on 64 bits and a bunch of keys on 64 bits. You can find them in Usuba typed as B64, so 64 bits. And then a rectangle XORs the plain text with the first key, call a function called subcolon, then shift rows, and does that 25 times to finally get the ciphertext. And you can find this in the Usuba code with the for loop, which calls shift rows subcolon and XOR with the key. Now let's zoom in on the component of a rectangle, so shift rows and subcolon, to see a bit more how our language works and how ciphers work in general. Oh, sorry. Wanted to say, keep in mind that our 64-bit input becomes 64 variables. Usuba allows you to write it as just a single variable and will expand it for you, so you don't have to bother with so many variables in your program. Now let's have a look at shift rows, for instance. Shift rows is a bit permutation from 64 bits to 64 bits. Since we are doing bit slicing, each of our bits is in a different register. So if you were to write a C implementation of shift rows, you would write a bunch of assignments, and that's it. However, in Usuba, you can notice that there is an underlying structure to the permutation, which you can exploit to make things easier to write. So what you are going to do is, instead of seeing your input as a block of 64 bits, you see it as 4 times 16 bits. So that's where the type comes in. You use 16 times 4. And then the 16 first bits of the output are the 16 first bits of the input. The next 16 bits are a left rotation by 1 of the next 16 bits of your input. Then you have a left rotation by 12, and then a left rotation by 13. So it's much more concise and easier to understand what's happening rather than in the C code. And on top of that, Usuba will not generate any code corresponding to that node, because it can do it can perform this instruction at compile time by just renaming the variables. So a permutation, when you are each bit in the variable, is just a renaming of your variables. Then you have subcolon, which I've presented earlier. It's a S-box of rectangle. Usuba allows you to write this as a table rather than a circuit to be closer to the specification, and it will replace your table with an efficient circuit during the compilation. Now, if we take a step back and look at the whole code for a rectangle, it fits in a single slide, which is pretty nice to have a cipher in just a slide. Now, some of you may think, well, I'm pretty sure you can write a code corresponding equivalent to this in C, and it won't be really awful. I don't see what you're talking about. Indeed, shift rows, you can write a bunch of assignment. Subcolon, just a few bitwise instruction. Rectangle, you could write a for loop to do your 25 rounds of shift row, subcolon, and XORs. Yes. And this is the kind of performances you would end up with. So you would be about 1.6 times slower than the code we generate with Usuba. And if you want performances on par with Usuba, you will have to write the ugly code I've shown earlier, which you don't really want to do. On top of that, Usuba can generate code targeting various SIMD extensions. For instance, the code of rectangle, we can compile it for IVX 512 extensions and have a very efficient implementation of our cipher. However, we can do even better. So there is an issue with bit slicing, which is registered pressure. So your 64-bit input of rectangle becomes 64 variables. And since you don't have 64 registers, you will have to do a lot of spilling. So typically, before any computation, you need to load your data from memory, compute, and then store them back in memory. We have two ways to avoid that. So generalization of bit slicing, which are vertical slicing and horizontal slicing. I'm going to start by presenting vertical slicing. So the idea of vertical slicing is that you see your rectangle, your input of rectangle as 4 times 16 bits, as you've done earlier. And each of these 16-bit elements goes in a different SSC register or any SIMD register. And then, like with bit slicing, you have some empty space in your registers. So you can take your second input and put it in the registers as well. And you keep doing so until your registers are full. Now, how do you compute on such data representation? Well, if we take shift rows, for instance, on the top right corner, once the first step of shift row is just an assignment, you have nothing to do, basically. Then you have a left rotation by 1, while SIMD extensions offer you instruction to shift or and shift left or and shift right your each of your 16-bit elements in your register at once. So with just 3 instructions, you can compute 8 left rotation at once, and same thing goes for the rotation by 12 and 13. On the other hand, you have another generalization of bit slicing, so horizontal slicing, where you are going to take your first 16-bit of your input and put each of them in a different element of your registers. Do the same thing for the next 16 bits, etc., etc. And then, once again, you have a lot of empty spaces in your registers, which you can fill up with some independent other input. And you keep doing so until your registers are full. And let's add some numbers, it will be easier to read. Now, the question, as always, how do you compute on such data representation? Well, the first step of shift row is still just an assignment, nothing to do. And then your left rotation can be done with a single shuffle instruction provided by your SIMD extensions. So with a single instruction, you compute actually 8 left rotation at once. and same thing goes for the rotation by 12 and by 13. If I sum up a bit about the parallelization strategy and slicing strategies we can use for rectangle, well, the basic one is bit slicing. So you take your 64 bits and each one of them goes in a different variable. Here, you have a lot of parallelism, a lot of throughput. Your permutations, so your left rotation can be done at compile time, it's very efficient. However, you have a lot of pressure on your registers, which is not ideal. On the other hand, if you do vertical slicing, V-slicing, each of the 16 bit element of your input goes in the different register. Now your pressure on your registers is much lower, and your left rotation are a bit more expensive, and you cannot really do arbitrary permutations, which would require a lot of shifts and masks. But on the other hand, you can also do no arithmetic operation, because SIMD extensions offer packed arithmetic operation like addition, which operate on each of the 16-bit elements of your registers. And finally, on the other hand, you have horizontal slicing, which still offer a low register pressure. You have more power for your permutation than in V-slicing, but you cannot do arithmetic operations. And which one you will use will depend on the cipher you are considering and the architecture you are targeting. In Usuba, all of this is directed by the types. So basically the same Usuba code, depending on which types you use, will produce a different sliced implementation. So if you do bit slicing, you type B64. If you are doing V slicing, you will see your input as 4 times 16 bits packed vertically. And if you do H slicing, you see your input as 4 times 16 bits packed horizontally. Now in practice, on shift rows, what does it look like? Well, the types are not specialized for any slicing type. You just write U16 times 4, and there is an implicit slicing direction within the types, which you will specialize at compile time to generate a code for each operator, which depends on which slicing you are using. So for your rotations, if you are using V slicing, you will generate shifts. If you are if you want to generate H slice code, you will generate shuffles, and if you are doing bit slicing, you will rename your variables at compile time. So the compiler does that everything for you. So basically and this does not just apply for shift rows, it's for the whole rectangle. So from a single code of rectangle, type U16 times 4, you can generate V slice code, bit slice code, and H slice code, targeting a lot of different architectures. So general purpose registers, SSC, AVX, AVX2, AVX 512. Compare which of them is more efficient, which will depend on the slicing type and the architecture, and then choose which one you want to use for your application. So I've mentioned earlier that if you just write some straightforward C code for your bit slice algorithm, it's not very efficient. There are a couple of reasons for that, and Usuba does a couple of optimizations, well, more than a couple actually. I'm just going to talk about a single one right now, which is interleaving. So let's take, for instance, a node which takes an input on 4 bits and returns 4 bits of output. The first bit of the output is the first bit of the input. The second bit of the output is the XORs between the first and the second bit of the input. And then you have 2 other XORs. And so you can see that you have a dependency between your XORs. So even though you have a superscalar CPU that can execute 3 bitwise instructions per cycle, you cannot execute those 3 instructions in a single cycle because of the dependencies. What we can do instead is to interleave a parallel independent execution of the ciphers of the cipher with the first one, which shares no dependency with the first one, therefore, and you can compute those two. You can compute those 2 executions of the cipher at the same time, and maximize the usage of your superscalar CPU. So basically, if you compute these 2 executions, those not 2 times at once, it will take the same amount of cycles than if you want to compute it just one time. In real life, you will very rarely have times 2 speed up, but rather between 15 and 30% speed up, which is very good on a cryptographic code. And Usuba automates this for you. Now if we take a look at how we perform compared to unwritten and optimized C code, so if the bars are on the left were less efficient than the unwritten C code, and if it's on the right, we're more efficient. So the idea is that the code we generate is about as efficient as unwritten C code, sometimes a bit slower, sometimes much faster. So for instance, here on Rectangle, we are much faster than unwritten C code because we use interleaving, which is not used in the most efficient implementation you can find out there. So Usuba performs well. And I'm going to conclude with kind of a summary of what I said right now. And also, it kind of acts like an overview of the paper. So we start from Usuba. I've talked about a bit of polymorphism and the type system here. Then we compile it, we boil it down to Usuba 0, a subset which is not polymorphic, with less high-level features. For instance, the tables and the permutation have been tables replaced by circuits and permutation done at compile time if needed. On Usuba 0, we apply a bunch of optimizations. So I've mentioned interleaving. Some other one as scheduling. We have two different scheduling algorithms, depending of which slicing type we are using. Then we generate C code, which is compiled with a standard C compiler to get some binary, and the paper goes more into the details of the evaluation and the comparison with the unwritten C code. And for future work, there are some optimization we could add to the language. For instance, counter caching, which I'm not going to detail too much right now. Then we can also add some front-end or back-end to the language. For instance, a front-end to add side-channel countermeasures to protect against power analysis or fault injections. So bitslicing is a good starting point for this optimization, and having the language to automate them is a good thing. And finally, at some point, we want to prove the end-to-end correctness of our compiler. Thank you.
Okay, so in the meantime, when people arrive, so I have two questions for you. One, have you looked at the cryptography project from Adam Shapala's group at MIT? So where they have been designing highly optimized crypto implementations for various elliptic crypto systems?
Yeah. So I've not looked at this particular project. We have not implemented a single elliptic curve in Usuba. Typically, Usuba is more designed toward block ciphers, and elliptic curves usually requires a lot of mathematical insights on how your elliptic curve works, which Usuba doesn't offer you any tools to automate this mathematics stuff. So I guess it's not a very good target for Usuba.
Any more questions?
Was there?
Yeah, why do I care about side channels, right? Like bitslicing can be used largely for group analysis.
Okay.
I just want to make it as fast as possible.
Could you repeat a bit louder, please?
Are there applications outside of cryptanalysis where you might care about this? This is awesome, but all I want is speed. I don't want my cryptanalysis to be like.
Yeah, but the best implementation from some ciphers are bitsliced. For instance, on AES, if you don't have ASNI instruction, the best implementation you can find are bitsliced. And even if you don't care about side channel attacks, if you want speed, you will have to bitslice it. Well, not bitslice, but edge slice it. And then on some other sides, so bitslicing can be done at kind of vectorization. And if you are doing, for instance, the Serpent cipher or ShaSha20, which are very widely used out there, bitsliced implementation is the fastest one. So it's not just about constant time.
Exactly right. So I just want to say is like I'll be doing 64. I don't have like 64 sessions happening concurrently.
All right. So yeah. So what's the question actually? So sorry.
I guess like why even care about side channel countermeasures? Like who cares? Make
Oh, really? Well, like cache timing attacks, which is a side channel attack, you can do it on a standard desktop computer. It's not like something very advanced. So I'm not answering. Sorry.
Let's thank the speaker again.